Nancy Kopo. In today's lesson of physical science, we are going to look at electric circuits. We are going to specifically cover two objectives. Though there are three objectives that are specified, we are going to look at two objectives. Our first objective from today's lesson, at the end of the lesson, learners should be able to calculate the effective resistance of 2 or 3 resistors in parallel. I'll quickly draw a parallel circuit of which this parallel circuit is going to have 2 resistors. We want to establish the effective resistance of the 2 resistors that are set in parallel so that we are able to see what is the effective resistance that is going to be offered, of course, by these 2 resistors. So I'll quickly draw a circuit. Alright, this is a parallel circuit which demonstrates 2 resistors that are connected in parallel. So what we are going to do is to assign the resistors. Say this is 2 ohms. I'll call it R1, the first resistor. And then I'll assign this as 3 ohms. I'll call it R2. So this is how resistors are supposed to be connected in a parallel circuit. I can give this source the voltage of 12 volts. So the source is what is going to drive the electrons, which is classified as the electric current. The continuous amount of flow of the electrons will accumulate, of course, within the conductor. And then when it reaches this point, it passes and then it will complete a loop. From here, same story, it will do the same thing. So in a way, the flow of the current is in that direction. So this is our I, the current, which is produced by the source. These are 2 resistors. Basically, if it was to represent as a bulb, what you would have seen is that when the current is flowing through, these 2, if they were representing bulbs, they will produce what we call light. This light will come as a result of a continuous amount of charge flowing. Therefore, to calculate the effective resistance of this parallel circuit, RT, 1 over RT equals to 1 over R1 plus 1 over R2. So this is, in other words, to say the formula to calculate 2 resistors that are connected in parallel. This is how we have to write the formula. So in a way, if we substitute the values of those distinct resistors that are set, we can have 1 over RT, which is the total resistance. And then here I have 1 over R1 will represent 2 ohms plus 1 over R2 is going to represent 3 ohms. And then from there, we are interested in finding the total resistance, which is classified as the effective resistance. Here we can write 1 over R2 equals 2. We simplify the right side of those 2 numbers that are given. We have 2 fractions, 1 over 2 plus 1 over 3, which means we look at the LCM. The LCM for 2 and 3 is 6. Therefore, 2 into 6 goes how many times? We'll have 3. Multiplied by 1, it will give us 3. Plus 3 into 6 will give us 2. 2 times 1 will give us 2. So therefore we have 2. From there we can have 1 over RT, which will equate to 5 over 6. Remember, The SI unit here is going to be ohms. The total resistance, which is going to be calculated here, is going to be RT. We take the reciprocal. This is going to be 6/5 ohms. And then this 6/5 is what we call the effective resistance, which is offered by those two resistors that are connected in parallel. So this is how we can find the effective resistance of two resistors. The sum of those two resistors that are connected in parallel will give us the effective resistance of the entire circuit. That's why in our formula, when we write RT, we are looking for the total resistance, which is offered by the sum of those two resistors, 2 and 3 ohms. Hence, it concludes to say, if we use the general formula that I provided, we substitute the values 1/2 plus 1/3 to summarize up to the total resistance, which is 6/5. It will give us this 6/5 is the effective resistance for those two in terms of parallel combination. Alright, having calculated the total resistance, the effective resistance of these two resistors, what we are going to do now is to look at how is voltage going to be distributed. Suppose we were to analyze the amount of voltage which is produced by these 12 volts. How is it distributed within these two resistors? Alright, what we are going to do now is to consider this formula. V equals to I times R. So this formula gives us the relationship between voltage, current, and resistance. Therefore, in this very circuit that we are having, what we are trying to do is we want to find out the relationship between the voltage which is produced by this 12 volts source in relation to these two resistors. We have V1, which will equate to I1 times R1. So if we look at V2, it will give us I2 times R2. In a parallel circuit, voltage so take note of this. Voltage is distributed equally. So what do we mean by this? It means if I have voltage total, this will equate to V1, which will equate to V2. And then if we had more than two resistors, this will imply that it will give us more than. So the Vn represents the unknown. In this specific exercise, we have two resistors. So therefore, if we have two resistors, our analysis is based on V1 and V2. Because at this point, when we talk of V1, we need to find out what is the current at that specific resistor. And if we talk about R1, what we need to establish is what is the resistance, the resistor rather, at that specific point. That's why we are saying in a parallel circuit, voltage is distributed equally. So I'll draw a circuit which is going to have two resistors in parallel, and then we are going to have one resistor in series. But at the same time, I just want to look at the point of sum of the total resistance, those that are classified to be in series and parallel. Let us consider this figure. Say this is our circuit. What is provided here is a combination of the series and the parallel circuit resistance, because we are looking at the effective resistance of this entire circuit. By default, what I'll do is I'll consider this as R1, R2, R3. So if we want, we may also extend it to R4, just to make it more interesting. So I'll have another resistor here, I'll call it R4. So this is just to create a bit of a good interest, because if we are talking about the overall resistance, remember we have R1, which is in series, plus, or let me use RT. I'll have R1 plus the sum of those resistors, 1 over R2 plus 1 over R3 plus 1 over R4. So basically it means the sum of 1 over R2 plus 1 over R3 plus 1 over R4, we can represent it as one unique resistor, but that total must be regarded to be in parallel, because the whole idea is that we want to look at the overall influence of these individual resistors onto the whole circuit, such that RT would now equate to R1. We agree that RT equals to R1 plus the sum of those resistors that are classified to be in parallel. So what we are going to do now is the sum of those individual resistors, 1 over R2 plus 1 over R3 plus 1 over R4. They will be represented by one unique resistor. I'll call it Rx. So basically it means this is going to be 1 over Rx. So here we are compelled to find the size of Rx in total, so to represent those three resistors. So this will translate to RT, which equals to R1 plus. Remember, the sum of those three resistors, R2, R3, and R4, is that unique Rx that I've indicated. So it means here we need to get the reciprocal of Rx, because if you can still remember what I said earlier, we are having a combination circuit, but our intention is to find the overall resistance. So therefore, this is my point of focus. If I have to be more specific, what I can do, remember I said we are interested in finding 1 over Rx, which will equate to 1 over R2 plus 1 over R3 plus 1 over R4. So therefore, before we substitute the value here, because remember this has to be a value which is going to represent the sum of those three resistors in parallel. So what I'll do is to consider another situation where I'll say 1 over Rx will equate to 1 over R2 plus 1 over R3 plus 1 over R4. So therefore, if we compute this one, this equation, so what we can do, I'll use this equation, 1 over Rx. Remember the Rx, we are representing it with those three resistors. So this is 1 over R2 plus 1 over R3 plus 1 over R4. Therefore, if we simplify the right side, this is 1 over Rx, which equals to, we look at the LCM, the lowest common multiple of R2, R3, and R4. So therefore, I'll write R2, R3, and then R4. Because we are looking at the variables that will go into R2, R3, and R4. So basically it means, if we're using numbers, it means we're looking for the lowest common multiple of R2, R3, and R4. So from this point, we can say, if I consider R2 and then I have R3, multiply by R4 plus. So here we have R3 into this, and then we have R2 multiplied by R4. This is basic mathematics, I suppose. And then R4 into the LCM, and then we have R2 and R3 multiplying with the numerator. So therefore we have R2 and R3. R2, R3, and R4. So these variables, they represent the unique resistors. So finally we can say our Rx will equate to the numerator. Now we take the reciprocal, so we have R2 multiplied by R3 multiplied by R4. This whole thing divides the top part, which is R3 multiplied by R4 plus R2 multiplied by R4 plus the last part, R2 multiplied by R3. So that Rx, remember what I indicated earlier? I said, so if you can still remember when I wrote RT, which equals to R1 plus summation of those three resistors that were classified to be in parallel. It means here we are now going to use that unique Rx, the reciprocal of those three resistors in parallel. So it means this is going to represent our total resistance. So if we're having values that could be substituted into the equations that I've already indicated earlier, the one where we had R1 plus a sum of those three resistors, this would have implied that the total resistance for the entire circuit is going to summarize to be R1 plus Rx. And again, point of emphasis is to say the Rx, once again, is the representation of those unique resistors. Because in this case, our Rx, remember, this is the parallel combination. And then from here, the R1 equate to a series resistor, and then lastly the RT for the entire circuit. We have come to the end of the lesson, but before we conclude fully, I quickly want us to look at the summary of the whole lesson. We looked at the parallel circuit, whereby we were provided with the general equation on how to calculate the total resistance in a parallel circuit. So we substituted the values 2 and 3, the resistors 1 and R2, of which we were able to compute, and then we got our total resistance to be 5 over 6. To be 6 over 5, because 5 over 6 is supposed to be taken as the reciprocal, and then after, with the total resistance will be 6 over 5. And then from there, we also looked at the voltage distribution, because we emphasize the point of V1, which equals to I1 times R1, and then we also considered V2, which equals to I2 multiplied by R2. So hence, voltage in a parallel circuit is distributed equally. The circuit, by default, I just now gave resistors that are not given unique numbers, or the numbers were not provided in the circuit. So we just now used mere variables to demonstrate the concept of the series and the parallel combination, but we are focusing on the overall resistance of a circuit, whereby I gave R1, R2, R3, and R4, whereas R2, R3, and R4 were classified to be in parallel, and then from there we got the total sum of those resistors in parallel, and then from there that gave us Rx. From there, if we proceed by working out the individual Rx, so mathematically speaking, it means we need to simplify the given fraction such that we look at the LCM, and then R2, R3, R4 were given as LCMs. So identity-wise, we are saying the three numbers that are given, they represent, or not numbers but variables, R2, R3, and R4, they represent the LCM, because we are talking about undefined values. Undefined to say we don't have numbers that are certified to represent those variables. So we just chose arbitrary values, random variables, R2, R3, and R4. So from there, if we take the reciprocal, and then this will give us Rx. And then having our Rx, we can now conclude that onto that point, the representation of Rx, we are going to look at the sum of R2, R3, and R4. Those in parallel, and then if we sum up them to R1, it will give us the effective. That's why from what I've written here, Rx is the parallel combination of resistors. So if you want, you may also have written 1 over R2 plus 1 over R3 plus 1 over R4. And then as such, you compute and then to get your unique Rx. So if you add it to R1, and then it will provide you with the effective resistance for the whole circuit. So this is how you can work out a combination of resistors so that you can generate the overall effective opposition which is going to be offered to the flow of the charge. So this concludes the whole lesson. Thank you so much for watching this lesson.